Please join me in welcoming Keith Vanderlinde.
Thanks very much for that intro, and thanks to everyone for coming out tonight. I'm here tonight to talk about doing some science in an odd place on the bottom of the planet at the South Pole. If you've never seen the South Pole, can we get the lights lowered a hint? This is what it looks like. It's absolutely barren. There's virtually nothing there. I do mean the actual geographic South Pole, not just Antarctica on the coast. This is 1,200 kilometers from the nearest coast, so from the nearest penguins. And it's just an ice field. As far as the eye can see, out to the horizon in every direction, flat, barren ice. The only way in and out is along a skiway on a ski plane. You can, in theory, ski in on foot, but it's a terrible idea. People have done it, and they continue to do it every year. A couple of brave souls make the trip, and they always show up horrifically frostbitten. So just don't do that. At the South Pole, there is a little piece of civilization. The Amundsen Scott South Pole Station, named for the first two people ever to reach the South Pole, or the first two team leaders, I suppose, is run by the US government as a scientific research base, just a facility where they can perform research of various kinds. So the station itself is divided up into a few sectors. There's the main station where everybody lives, eats, sleeps. There is what's called the clean air sector off to one side. That is upwind from the station, and you end up having some of the cleanest air on Earth. There is absolutely no one upwind from it to pollute it. So it's just pristine air, and it's a good spot to take measurements to get good, stable measurements of what's going on in the Earth's atmosphere. So back in the day when CFCs were a big problem, this is where a lot of the measurements were made. Nowadays, CO2 is a big problem, and methane in the Earth's atmosphere. A lot of measurements come out of the South Pole Station clean air sector. I worked over in what's called the dark sector, not because it's any darker than any others, but because it's radio dark. You're not allowed to have walkie-talkies, cell phones, Wi-Fi, computers, anything that generates any sort of radio frequencies of any sort. It's a radio dark site because of the research we do there. There's one thing that everyone always wants to know whenever I say, at the South Pole, and the answer is yes, there is a pole. It's candy striped, and there's a nice silver ball on top. This isn't strictly the real South Pole. This is the ceremonial pole. It's placed in a nice location right in front of the station with all of the flags of the nations that are signatories to the Antarctic Treaty on it, around it. The real pole is actually a hard thing to place because this is all ice. You're on a glacier 3 kilometers thick, and that glacier is slowly flowing out to sea. So every year, someone has to come along and pick up the pole and move it somewhere else. So they have teams that fly in specially to do that. The actual pole looks like this. It's a steel rod jammed in the ice that they reposition every year. It moves about 10 meters a year. So the station is flowing out to sea fairly quickly. This is a picture I took when, oddly, I was the only Canadian on station, and I did not bring that flag. I have no idea where it came from. No one ever fessed up to it. It just turned up one day, so I ran outside and took a bunch of photos, and then it was gone in the morning. But I'll take it. I was down there to work on this guy, the 10-meter South Pole Telescope. That is the official name. It's the South Pole Telescope because we're very good at naming things. It's a telescope at the South Pole. The South Pole is an incredibly difficult place to build a telescope. One, everything's on ice. It's a 3-kilometer thick sheet of ice underfoot. Two, it's a long way from nowhere. Three, it's awfully cold most of the year, all of the year. It's not where you would immediately think of building a great big 10-meter radio dish. So to understand why it's down there, I have to go on a few diversions, and then we'll get back to the South Pole Telescope in a bit. First, though, we'll jump up 50 years earlier, or 52 years ago now, to a telescope in New Jersey. This is a funny-looking telescope. You can think of it as like an ear horn, one of those old-school ear trumpets. Light comes in here, gets focused up into this box where they have detectors. This was actually a communications antenna. This was a Bell Labs facility. They were sending signals, bouncing them off balloons in the upper atmosphere, trying to send long-distance communications and set up some better early form of cellular telephones, essentially. And the two engineers working on it, Wilson and Penzias, could not for the life of them make sense of the noise that they were seeing. They kept seeing more noise than they should. And they fought it for years, scraping extra pigeon dung out because they were convinced it was probably the pigeons nesting in it that were causing the problem. It's a long story about how careful engineering can work out in the end, because ultimately they published a paper with the absolutely fascinating title of a measurement of excess antenna temperature at 4080 megacycles per second, which a couple years later won them a Nobel Prize. To understand why, that's why I have to go through those diversions, and this all plays into the story, as you'll see. So the first one, many of you are familiar with light, at least the rainbow, the Roy G. Biv, but many of you probably know this is only a tiny portion of the rainbow, right? There's ultraviolet off the top end, there's infrared off the bottom end, there are X-rays past ultraviolet, and there's actually a whole spectrum of light beyond what our eyes can see. Just, a continuum of colors well beyond what we're built to pick up. All the way from gamma rays at the highest energies, through X-rays, ultraviolet, the little band of visible light that we can see, infrared light, microwaves, and down into radio. All of these now are used actively by astronomers for studying the universe, but to actually look at them, the only ones that we can see ourselves are the visible ones, so we need to build special instruments to look at all the others. This is what the sky looks like in visible light. If you take the celestial sphere and unwrap it, just take it and flatten it out. I even have a picture to show that. So if you take a sphere and lie it flat, it makes this funny egg shape. So this is what visible light looks like with our galaxy running through the middle. This is in galactic coordinates. Hopefully people are familiar enough that if you go out of the city, you can see the Milky Way running overhead. It's really beautiful. If you haven't made it out of the city, you absolutely should. Find somewhere dark and go look at the Milky Way. But you can look at the sky in all these bands. In gamma rays, we have excellent gamma ray observatories in orbit around the Earth measuring the sky. Mostly what you see is our galaxy and these little hotspots that are active galactic nuclei, matter falling into supermassive black holes in other galaxies. X-rays, we don't have a great map. Mostly what you see is high-energy stuff from our galaxy, supernova remnants and things like that. UV, we have a terrible map so far, mostly just because the sun puts out a ton of UV energy. It blinds any instrument we try to use. So we still don't have a great way of looking at the sky in UV. Continuing down, we get down to visible, the good old familiar Milky Way with dust lanes blocking the starlight, a couple of smaller galaxies, dwarf galaxies, the Magellanic Clouds that are orbiting ours. If you push further, you get into the infrared sky. This is kind of where most telescopes nowadays tend to operate because you don't have to worry quite as much about the dust lanes, the dust extinction in our galaxy. And if you're doing things like looking for exoplanets, it turns out that you actually get better contrast. You can see the exoplanets more easily around their host stars in infrared light. Down at the far end is radio waves. So radio telescopes look at a sky that looks something like that. It's not starlight anymore. They don't see much light coming directly off stars. Most radio waves that astronomers study come from, diffuse structures. What's called synchrotron radiation from loose electrons spiraling around magnetic field lines. It's a very different piece of the universe, or of the galaxy at least, that you're looking at when you look at radio light. So you may have noticed that I skipped one, the microwave light between infrared and radio. And there's a reason I skipped it, because it's the one I'm here to talk about today. This is what a picture of the sky looks like in microwaves, and this is not a display error. This is the picture. It's fueled in industry. It's really weird, right? There is no galaxy visible anymore. There's just this uniform glow from every direction, the whole sky shining down at you brightly from every direction all the time, 24/7. Nothing really obstructs or blocks this. The whole universe glows in microwaves. And this is a measurement that sort of raises some questions. So a quick diversion, again, into cosmology this time. We've known for almost 100 years now that the universe extends beyond our galaxy. 100 years ago now, people actually thought most of the universe, or most astronomers thought that the universe was contained in our galaxy, that our galaxy was the extent of it. But then in the early 20s, Hubble went out and made his famous measurements to show that, in fact, all the spiral nebulae were other galaxies. They were enormous pools of matter, vastly distant, and discovered that, the universe is much bigger than we thought. And then he went out and measured the redshift of everyone. He measured how it was moving relative to us. And he came up with this weird measurement that every galaxy, except the really close by ones, is flying away from us. And the farther away from us they are, the faster they're running away from us. Everything in the universe seems to be receding from us, except for our own little backyard. This is a weird thing to see, and at first glance, it just looks like we're the least popular people in the entire universe, which by this point of cosmology, we'd sort of rejected any anthropocentric models where we live at the center of everything. So we needed some other way of understanding this. And conveniently, this was shortly after Einstein had come out with his theory of general relativity, which said that space and time were not really fixed things. They could stretch and squish and bend and twist and do all sorts of strange things. And particularly, this observation can be understood not as galaxies flying through space away from us, but as space getting bigger. So the space separating any 2 points grows over time. And that naturally leads anyone, anywhere in the universe could make the same observation, and it would look like everything was flying away from them, because all the space is getting bigger, moment by moment. So this is our model of the expanding universe. This is currently what we hold. It is the best model that we've found to explain our observations of how things are moving through the cosmos. It took a couple of years for anyone to take the next logical step and think, wait a minute, if the universe is expanding, if space is getting bigger moment by moment, then in the past it used to be smaller. It's a fairly natural conclusion that, if things get bigger going forward, well, that means that they're smaller going backward. So if you have this universe with a couple of galaxies sprinkled through it, and you rewind the clock, well, those galaxies are closer together. The space is smaller. And you rewind the clock farther, and they're closer together still. And rewind the clock farther, and eventually everything sort of crams down into the same point, into some hot, dense universe 10, 15 billion years ago. Nowadays, our best estimates put it around 13.8 billion years. This is where the notion of a Big Bang came from, because if you take this picture and you play it forwards, you start with some sort of giant fireball universe where everything is a hot, dense plasma, and it expands out. Every part of it expands and gets larger and cools off and collapses into structures. And this looks like an explosion in some sense. It's not a traditional explosion, but it's analogous in ways. And this led the main critics of the model to make up a name to make fun of it, that the whole universe, sure, evolved from a Big Bang. Yeah, great. But yeah, it seems to have. Luckily, we're not just left to models to understand this, because light is very fast. It's 300 million meters per second, right? It's the fastest thing in the universe. It's the fastest anything can move. But it's not instantly fast. On Earth, you tend not to notice it. Phone calls go around the Earth many, many times in a second. If you look farther afield, though, you do notice it. Sunlight does not arrive at Earth instantaneously. When you look at the sun, you aren't seeing current light. You're seeing old light. It takes about 8 minutes for that light to get from the sun to you. So the image that you see of the sun is made up of light that left the sun 8 minutes ago. You're seeing an old picture of the sun. Whenever we take pictures of the sun or anything like that, it's old information. We get a snapshot of what was going on 8 minutes ago. Again, not a big deal in our backyard. In the solar system, 8 minutes, yeah, okay. It's difficult if you're trying to send people to Mars and trying to talk to them, and Mars happens to be on the far side of the sun. Having 15-minute delays is a pain. If you've ever had a phone call with a half-second delay, you know how difficult it is to communicate. But when you go farther afield, it gets worse. Right? The next nearest star, Proxima Centauri, is 4.2 light years away. A light year is how far light goes in a year. So this means when light leaves Proxima Centauri, it takes 4.2 years to get to us. So we see that star as it was 4 years ago, 4.2 years ago. If there are little green aliens there looking at us, listening to our radio broadcasts, they don't see today's Earth. They see all the light that left here 4.2 years ago. They see an old version of the Earth. So they're still eagerly awaiting the birth of the first royal child. Farther afield, it gets worse. If you look at the next nearest galaxy, so outside our Milky Way, look off to Andromeda. It's 2.5 million light years away. We see it as it was 2.5 million years ago. You can play the same trick and ask what was going on Earth 2.5 million years ago. If you trust Hollywood, it looks something like this. Not quite accurate, but you get the idea. So here's a rough drawing of our galaxy. I'm just going to zoom out from that and see what we know about our universe. So here's our galaxy. We can zoom out one step, and you can see some dwarf galaxies, part of our local group, that are orbiting us. These are just smaller clumps of stars and matter, which are caught in our gravitational field. If you zoom out, so now I'm already on very large scales, right? The galaxy is something like 100,000 light years across. So this is a big structure. Here, this bar is now 100,000 light years. So if you look out to, say, here, you're looking back in time 200,000 years. If I zoom out again, there we are at the center with our little clump of galaxies. There are two other large galaxies that make up our local group, Andromeda and the Triangulum galaxy. And they also have a bunch of small dwarf galaxies around them. This is, we're looking at very large scales now. This is that 2.5 million year sort of scale that you're looking back in time. But we've seen much farther than that. You can zoom out farther. This is now 10 million light years for each of these rings, and you can start to see galaxies forming into clusters of galaxies. You can start to see what's called the large-scale structure of the universe, where things clump together in giant gravitational halos. Here we live in our local group. We're just one point now. The Virgo cluster is nearby. It takes up a large chunk of the sky. But often these things are hard to see because they're mostly empty space. They've got tons of galaxies in them, but even galaxies are mostly empty space. If I zoom out again, now 100 million light years for each of these little bars. You can start to see large structures forming, big voids, big walls, large structures that make up the large-scale structure of the universe. This is what it looks like when we actually go ahead and measure it. Each point on this represents a galaxy, and these are different surveys looking in different directions. Two of them are actually simulations, but I defy you to figure out which are which. It makes up what we call the cosmic web. You can see this sort of filamentary, spongy sort of structure that makes up the distribution of matter. So this is all out to a few billion light years away. It's reasonable to ask, how far can we see? How big is the universe? And the thing that I've been trying to build up to is that as you look farther and farther and farther out, you're looking at older and older and older light. We don't see an edge. Before we get to the edge of the universe, we get to the beginning of the universe. We run out of time in which to see back before we get to the edge. So we see that hot, dense fireball universe. When you look far enough away, you're looking far enough back in time. That's what these guys saw with that strange telescope that had too much noise sitting in a cabbage patch in New Jersey. That's why the microwave sky looks completely gray. That's thermal emission. It's the glow of the early universe. It's the leftover light coming from farther away than anything else and just hitting us now from when the universe was a baby. And that's why we built the South Pole Telescope, to study that, to study the oldest light in the universe. It's called the cosmic microwave background because, again, we're terrible at naming things. It's visible in microwaves. It's farther away than everything else, so it's background. And it's, cosmic, way out there. So the South Pole Telescope looks something like this. This is what it looked like when it was first built. Like I said, 10-meter dish. It was constructed a little over a decade ago. I guess it was, a little over a decade ago. Light comes in. This is an off-axis Gregorian for people who are telescope dorks. Go team. Bounces off the primary mirror and into a receiver cabin where our camera sits. Inside the cabin, we have a complicated system, mostly because that microwave light, while it's really bright, it's still actually quite weak relative to other things. There's just very little energy in microwave light. And if you're trying to see it, you have to really put on blinders and shield yourself as well as possible. When people build infrared telescopes, one of the things they have to deal with is that most things glow infrared light, right? I'm constantly glowing in infrared. if I have a camera that's at room temperature, it's glowing. And you can imagine if you had an optical camera that was glowing, that would not be good. It would blind you to all the things you wanted to see. In microwaves, it's much, much worse. The cosmic microwave background is 3 Kelvin, so minus 270 Celsius, roughly. So anything warmer than that is brighter than it, glows brighter than that, which means our optics system, our camera system, has to be cooled off enormously. The whole thing lives in a cryostat, a big metal can about the size of a Volkswagen Beetle, and it's cooled down to between 1 and 10 Kelvin, different parts of it. So 270 degrees below zero. There's a large secondary mirror that focuses things down to the camera. Microwaves are also tricky to detect. Like I said, microwave light doesn't have a lot of energy in it. Unless you turn on a huge light bulb of microwave light, which we'll get back to. There's just not much energy there. And you can't use a normal cell phone camera to try and take a picture of it. Instead, we use bolometers. So bolometers are something that have been around for a long time. They were invented back in the 1880s by Samuel Langley. And the idea is that you take a piece of metal whose resistance, it's electrical resistance. You build a little circuit around it and measure its resistance. And then if it heats up, that resistance changes. And if it cools off, that resistance changes. And you just measure its temperature by virtue of its resistance. And the first one, built in 1880, was so sensitive that it could detect thermal radiation from a cow in a field a quarter mile away. It could see that the cow was glowing. If you aimed it at it, it would warm up enough from that cow glow to actually heat up. And there's a handy little limerick that I was taught to help you with this. It's that, if I can do this, Langley invented the bolometer. It's really a type of thermometer. It can measure the heat off a polar bear's feet at a distance of 0.5 kilometer. So now you know. We basically do the same thing now, only we've gotten fancier. Instead of using a platinum strip that we heat up or cool down, we use superconductors. So you take a piece of metal and you cool it down almost to absolute zero until it goes from being a normal conductor with a resistance to a superconductor with zero resistance. And when that happens, there's this sudden drop in resistance, this extremely strong response to temperature. And we cool it to exactly this point so that a tiny, tiny, tiny shift in temperature, just a couple of extra photons coming in, warm it up enough detectably that we can see this. And this gets you down to ridiculous sensitivities. You can see something like a billionth of a watt of increased energy loading, which is an incredible number. And it means that this is essentially a noiseless detector. These little guys they essentially make a perfect image of the sky almost instantly. They're manufactured. This is what these things look. So the main part is only about 1/10 of a millimeter. They're small little devices. They're placed in the center of some sort of web that absorbs the photon, that absorbs that microwave light and heats them up. This is what we call a spider web layout. And then these are patterned and manufactured into wafers containing hundreds of them. So this really builds off computing technology, just circuit production. We use essentially circuit fab facilities. So we take hundreds of these with their little absorbers on each wafer and pack several of those into a camera. And this is what a microwave camera looks like. It's not like a cell phone camera. It's made up of thousands of these little detectors, and they sit right here at the focus of the whole thing, and they're cooled down to within an inch of their life. They run at less than a Kelvin, so it's about 1/4 degree Kelvin. You may have noticed I still haven't answered the question that I started with, which is, why are you in Antarctica? There's a really easy answer to that, which is that water absorbs microwave light. Water and water vapor are opaque to microwaves, so you can't see through them at all. And that's why your microwave oven works, right? Your microwave oven has an extremely powerful microwave light bulb in it that just shines microwaves into it, and your food has lots of water in it that absorbs all those microwaves and heats up. So the fact that microwave ovens can exist tells me immediately that we can't operate anywhere like this. If you have clouds, if you have water vapor, if you have humidity of any sort, you will not be able to see out to space. It just blocks your view. Now, this blocks visible light. We've all seen a cloudy day. You can't see the stars. Not a big surprise. but even a little bit of moisture in the air does it. It does not have to be cloudy. So we really need to get somewhere where there are absolutely no clouds. There are a couple ways of doing this. One, you can go high up. Try to get above all the moisture. And if you plot an elevation map of the Earth, there are a couple of spots that stand out. The Himalayas are nice and high, the Andes are nice and high, but there are these two whole big chunks that are giant red blobs. Greenland and the Antarctic are both extremely high up for the same reason, just because there's ice piled up on top of them. There's a giant snow pile on each of those land masses. Antarctica is actually the highest of all the continents. The land level is only a few meters above sea level. The ice level is 3 kilometers above sea level. So the whole thing is essentially on a mountaintop. The other thing you can try to do is go somewhere where it's actually dry. Stay away from Hawaii in the tropics. So if you plot the moisture in the atmosphere, purple being dry, red being wet, you can see the Antarctic and Greenland again are both quite dry. And same reason. All the water is under you. It all froze and made that giant snow pile. So that's fine. Water under me doesn't block my view. I have no issue with that. And that really is the reason that you go to the Antarctic. You can get high up above much of the atmosphere. You can get away from all the water, and you get a crystal clear view of space. There is one other reason, actually, which is that there's only one day-night cycle a year at, either the Antarctic or the Arctic. The sun at the South Pole rises on September 21st and sets on March 21st. That's it. In the rest of the world, it comes and goes every day. And every time it comes up, it warms the world up a little bit. All of the air heats up, expands, rises, and then at night it cools off, compresses, falls, and it's always shaking around. You got all these turbulence cells built up. Air is constantly being stirred up. And that leads to funny visual effects. If you look out at stars, they twinkle. That twinkling is because of turbulence in the atmosphere. In the Antarctic, nothing twinkles. In the dead of winter, the sky is dead still, and there is no turbulence in the air because there's no warming, cooling. That means we get a slightly more stable view, which, great. The downsides are fairly obvious. You can only get in and out 3 months of the year. In the summer, which summer season just started down there, I think the first flight was in last week. It gets up to minus 30. So that's as warm as it ever gets. This is the only time that you can get new people and new supplies in to really try and build new experiments, repair old experiments, do what you have to do. Because at the end of the summer, everyone gets loaded on planes and they leave. This is the last flight leaving. Oh, this is one of those ski planes, by the way. You can see the planes are run by, of all places, the New York Air National Guard. Why they operate in the Antarctic, no one knows, but they fly scientists in and out. According to the Antarctic Treaty, there are no military operations allowed, so they're there strictly as civilians doing scientific research. This picture, though, this is the last flight. I took this picture, which means I'm not on that plane. I was one of the lucky few who got left behind to winter over, for the simple reason that nothing works properly when it gets down to minus 70. Everything breaks. Machinery simply can't stay lubricated. It can't stay warm. Fans seize up. Belts freeze and snap. Everything breaks, except people. People are fine. Just leave them behind. People can just put on another jacket. It turns out they get by surprisingly okay. So this is a picture of me only a few weeks after last flight. This is long before it got cold. And you can see I'm already frosted over pretty badly. It becomes dangerous to blink quite early. To give you an idea, this is the weather station in August, so nearing the end of winter, almost coming towards sunrise. And the wind chill that day had just dropped below minus 100. So it does get slightly harrowing, let's say. This sort of shows you the things that I was talking about, though. It's incredibly cold. The barometric altitude is over 11,000 feet, so over those 3.2 kilometers, something like that. It's really a beautiful place to do astronomy, except that you have to go there. This is, again, just before sunset. I thought it would be interesting to show what you wear. To start, you have to keep your head warm, so balaclava is a good start. And then you always have a neck warmer as well, because just a balaclava is not going to do it. One layer of fabric, never going to do the trick. And then a hat on top, same reason. You get left with these giant Canada Goose jackets. They're not the standard Canada Goose jackets that you can get in North America. This is actually roughly one of the North American ones, but this is what we call the Little Red. There is also a Big Red jacket, which extends down well past your knees and makes you into a Michelin Man style thing. But Big Red is the sort of fundamental thing. It's got a nice big hood that covers your head. For your feet, you have to wear a pair of liner socks, a pair of giant socks, a pair of huge space boots. For people who haven't worn felt space boots, they're pretty fun. It's felt a couple of inches thick all the way around your feet everywhere, and you have no maneuverability at all, so you're just sort of bouncing around like you're on the moon. For your hands are probably the worst part. You wear, normal liner gloves and then some work gloves, in some mittens, in some more mittens. And by the time you get to the end, these mittens are not very dexterous. They're just a tube that you put your arm in to try and warm it up. And if you have to do work outside, these aren't going to cut it. So you have to sort of quickly be able to strip down to fewer layers of gloves. But you can't go down to bearskin, because that'll freeze solid in a few seconds. So there's this whole system that you get into of what you can take off for what work. And that's always an experience. Like I said, you have a Big Red. Often you wear large insulated overalls. It's a better way to go. And long johns and several pairs of long underwear. You can see here I have goggles on. You may be able to see that they're completely frosted over. I can't see anything. Goggles are completely useless there. They frost over immediately. The moisture off your eyes just sublimates or evaporates and freezes instantaneously. So there is no point wearing goggles. Every year, several people on the station make it their mission to try and design a pair of goggles that will work. And they get these complicated systems with snorkels blowing through and heating packs with fans blowing everywhere. No one has ever managed to make it work. But there's, if you can figure it out, there's $20 in it for you. So through winter, you just throw out your goggles and pinch things closer together. It makes it harder because not blinking becomes an issue, but blinking freezes your eyes shut, and it's tricky. People often ask what sort of, so you saw penguins, or in some cases, polar bears. And, they have an image like this for what's going on. No. Penguins live on the coast, 1,200 kilometers away, but, fair guess. Polar bears live in the north, much further away. Children are actually banned from the South Pole. Just by the U.S.'s decision. They run the station. They don't allow children on station. Animals are banned, dogs particularly, by the Antarctic Treaty. You aren't allowed to bring external fauna or flora in because they're afraid it will disrupt the natural fauna. There are no hills of any sort, so everything about this picture is as wrong as it could possibly be, which is why I like to put it up. The closest thing that we have to life there are these little guys. They're snow tumbleweed. If the weather works out just right, a storm blows through and you get a little bit of moisture in the air, and then there's a hard freeze, so it drops quickly, so that you get hoarfrost, grows up off the ground, and then just the right wind comes in, it will snap it off and tumble it. And occasionally, you end up with just armies of these snow tumbleweed rolling by. These things are called yucca-marimos. They were first described by a Japanese team, not even 20 years ago. But they're absolutely amazing little things. They have the texture of cotton balls, but they're made of ice. Really odd, and I was lucky that we had a couple of them my winter. Normally, they only come every 2 or 3 years. Also, not alive in any way, just to be clear. There is no life at the South Pole except for people who get left behind. Here is sunset approaching. The sun just spirals around and then gets lower and spirals and then circles on the horizon, and then it's gone and it spirals below the horizon. And then it comes back 6 months later. This is the sunset. You get an absolutely beautiful sunset because it takes sort of 2 weeks from when the sky starts to turn pink to when the thing goes away. It's lovely. Right after the sunset, though, everything freezes over. You've lost radiant heating, and ice just condenses everywhere. This is the laboratory that you work in the dark sector where the telescope is. Again, not because it's darker there, just it's radio dark. So this is known as the dark sector laboratory, which sounds cool. It frosts over very quickly, and you actually have to plug up these warm and cozy looking windows. We have to block out all that light because there are people who are doing light-sensitive experiments, looking at the aurora particularly. This is where I worked most days. To get there, you have to walk, because again, machinery is frozen, nothing runs. It's about 1 kilometer away from the station, and you find your way by following the flags. We use flags instead of a rope, because ropes can get cut. On the occasional days when machinery does move around, they tend to break everything. These flags are placed 10 meters apart, and in a storm, sometimes, you can't see that many of them. This is early on a stormy day. Later in that day, you couldn't see the next flag from the current one, which means you cast off, and then you don't know where you're going. And particularly when you trip and fall, because you can't see the ground and all of the new snowdrifts, you get up and you don't even know which way you're facing. The reason we use flags is because you can hear them. They blow in the wind, and you can hear the flapping almost independently of how dark it is, and you can just aim for the flapping noise. As it begins to get dark, you get a bit of relief, actually, because of all things, the moon comes up. And I guess for astronomers in the audience, you know how bright the moon is. You have a good sense of how much it ruins your view of the sky, but it also illuminates everything beautifully. So this is the moon rising next to the telescope, not the sun. And this is what the world looks like in moonlight. It's fully lit up. You can see perfectly well. You have color vision again. The only way you can really tell that that's a moonlight shot is that the stars are visible. So every 2 weeks the moon will come up, and because of the geometry of the whole system, it's always full in the winter, and then it will set, be down for 2 weeks, and then 2 weeks up, 2 weeks down. And you start to rely on it as a sort of a surrogate sun. It becomes your new day. So I got to the point where I would occasionally ask people, is the sun up today? And they were like, no, it's been dark for 4 months. What are you talking about? But no, you start to think of the moon as the sun. So while you're left there, you do have responsibilities. I was there, like I said, to fix the telescope every time it broke. But that's not the top responsibility. The first thing that you have to do is make sure that everyone makes it through the winter, because it is a dangerous place. You have regular safety drills, training drills of all sorts to make sure that everyone gets out. Oddly, the biggest risk is fire, because even more than cold, it's dry there. The South Pole is the driest place on the planet. That's why we're there. And everything desiccates. So all the wood, just anything that you have there is as dry as it can possibly get, which means that shocks build up everywhere really quickly. Everyone knows that in winter here, you build up shocks as you scuff around, and you electrocute yourself when you try to touch the door. Never did I take a cookie at the South Pole without it shocking me. Every cookie in that place shocks you, and it's just... like I said, I was there to run the telescope, though. So most of my day was spent operating or fixing the telescope, because the telescope does break a lot. This is me with a stethoscope on, listening to one of the motors to figure out why it had seized up. There's a lot of fixing motors. Anything mechanical, anything with lubricant on it, dries out, breaks, seizes, overheats. Everything goes wrong. Everyone pitches in and does chores throughout the winter, because we can't, you can't afford staff whose job is dedicated to that. Everyone really does have to pull together, and you spend time in the dish pit, you spend time cleaning the bathrooms, you spend time doing, well, everything. Everyone pitches in. And then the telescope breaks, and you go fix the telescope again. This is me fixing a different motor, sticking a screwdriver in it to try and get it moving again. Don't try it at home. If things work out, if you do start to get some free time and some decent data and the telescope's working, you actually get a chance to look at it. This is one of the real reasons that I volunteered to do this, because it gives you a first crack at the data. It takes a while to get this back to North America. Mostly it actually transfers back the next summer when flights show up to take hard drives and fly them away. But this is what our data looks like. It doesn't look like a very pretty picture, but this is because our camera, this fancy sub-Kelvin bolometer system, It's not like my phone with its 10 megapixels. It was 600 pixels, and that is state of the art. The newest one that we just deployed now, 10 years later, is up to 10,000 pixels, so a 10 kilopixel camera, 1,000 times worse than my pocket camera. To get around that, to make an image, you can imagine 100 by 100 image doesn't make a very nice one. It's like those terrible little emojis or something on your desktop. We don't just take one picture. We take a picture with this camera 100 times a second, 117 times a second actually, and then we swing it around madly and stitch everything together into one giant panorama. Essentially, that's how this operates. We take 100 pictures a second for 3 or 4 years and then stack them all together to make a real image. So this is what 1 bolometer shows you as time goes by. This is the temperature that it's seeing. This is how hot it is as it goes over brighter parts of the sky, fainter parts, brighter parts, and it's picking up more or less light, heating up or cooling off. And then the telescope breaks, and you have to go fix it. This picture in particular, this is not a nice motor to fix for anyone who ends up there. This white part is sitting at ambient temperature. It's the outside temperature, so it's minus 70, and if you stand up, your head freezes to it. And that does not feel nice. Yeah. All things cooperating, you actually get to make sense of that data and do some sort of science. So what is the science that we're trying to do? You might look at this picture and say, well, come on. How do you do anything with that? It's just gray. There's nothing there. But there is a lot there that I've hidden in this. This is what the sky looks like. But if you turn up the contrast enormously, you can start to see details on it. So if I turn it up by about a factor of 1,000, it looks like that. So this is where I've just taken the dark bits, made them 1,000 times darker, the light bits, made them 1,000 times lighter. And a couple things pop out. First of all, you can start to see our galaxy in this reddish color. This is false color. It's all microwave light, so we just convert it to look to be in visible light. So this is the galaxy. That's not stuff that we're interested in. It's not the oldest light in the universe. It's local. It's a few thousand years old only, maybe a few tens of thousands. This dark light patch is because we're actually moving. We have a proper motion through the universe, and it's a Doppler shift. We're moving into some of it, so it gets higher energy, and we're moving away from another part, so it's lower energy. We're moving away from this part towards this part. That's something that we can model beautifully, and we can just subtract it off. So if we subtract it off and turn up the contrast another factor of 100, it looks like this. And this is when you start to see really the old light, that old primordial universe, the early universe. There's still this stupid galaxy in here, but the galaxy has a different color. It has a different spectral shape than the CMB, so you can just filter it out. We apply filters, and you can remove that, and you end up with something that looks like this. This is a picture of the early universe. This is a full sky map. The South Pole Telescope can't see the full sky. It's at the South Pole. It can only see half of it. And we don't even look at half of it. We actually look at a really relatively small patch, only about 5,000 square degrees. 1/8 of the sky? Yes. This is what our patch looks like. And we only look at that one little bit, but we look at it in really high resolution. We can see a lot of detail that the telescope that made this full sky image can't pick up. So if I take this and I zoom in on a chunk of it, it looks something like this. Here's the full moon for scale. So this is a really large piece of sky. Right? This is a big chunk of the universe that we're looking at. But you can see this sort of cloudy structure, this puffy, gaseous sort of thing going on. That is because what you're looking at here, this is an honest-to-God picture. Right? This is, all we've done is we built a camera, we exposed it to light that came in from somewhere. That's exactly what my cell phone camera does. This is just sensitive to light that happens to be coming from farther away. This is what the universe looks like if you can see really far away, or if you prefer, really far back in time. This is what the first few 100,000 years of the universe looked like. This is a photo of the universe when it was 0.003% of its present age. And that, to me, is kind of amazing. Right? This is the oldest light, and it's from a long time ago. And for comparison, this is me at 0.003% of my current age. So when you look at this, it's really a baby picture of the universe. It's showing what the universe was like really early on. And just like I'm pretty easy to understand in this picture, I mean, all I want to do is eat, sleep, and poop. The only information you really need is, I'm a boy. This is a relatively easy universe to decipher. It doesn't have stars or galaxies or planets or people or any of the complicated stuff yet. None of that has formed. This is a much, much, much simpler universe, and we understand the physics in it much better. So by studying this, we can get a good handle on what's going on in those first, 300,000 years of the universe, and what physics is at play, what material is required. And it's pictures like this that tells us, well, you need 6 times as much dark matter as regular matter. Matter that doesn't care about light, that just doesn't interact with light. Doesn't reflect light, doesn't absorb light, doesn't emit light, doesn't do anything with light. It couldn't care less about light. Otherwise, it's the same as matter. And there's a lot more of that than the stuff we're used to. That comes from looking at what is going on, the structures in here. But there's other stuff that you can do. And the stuff that I was interested in this for was actually to use it as a backlight to look at the later universe. Because it is a background. It comes from everything else. It comes from farther away than everything else. And because of that, it travels to you through the whole visible universe. It passes every structure in there. And every structure has a chance to mess with it a little bit. If you have a giant clump of mass, that gravitational field distorts it slightly. It lenses it. If you have a hot cloud of gas somewhere, that can blue shift it. It will absorb some of those photons and knock them up to higher energy. So particularly, I used this to study the growth of structure. This is showing 3 sort of chunks of the universe at different times. Early in the universe's history, it was a fairly uniform, smooth, fuzzy gas, right? Just like this, I had to turn up the contrast 100,000 times to see anything. In the early universe, that's basically how it was. And then as the eons passed, over billions and billions of years, the little details here, the little bits where there's a tiny bit more material, gravitationally attracts a bit more material from the surrounding area. And that's a feedback loop, because now there's a lot more material there, so it falls in faster. And now there's a whole lot more material there, so it falls in even faster. So you go from these tiny little seeds of structure in a very uniform universe into that filamentary structure, that spongy structure that we see when we look out today. So we understand the physics of that fairly well, except that it's extremely sensitive. How this actually evolves is super sensitive to everything, not just the physics that we understand, but also the stuff we don't. It's really sensitive to exactly how that dark matter works, or particularly how the bigger mystery component of the universe, dark energy, works. Get back to that in a bit. But looking at this, the way that you can measure this, first, it's hard to make an image of all the material in the universe. That's just caveat. So instead of doing that, we don't try to. We just try to pick off the big peaks here, these bright spots, these intersections in the spongy filamentary network. And those correspond to these big clusters of galaxies, where you get 100 or 1,000 galaxies all clumped together and gravitationally bound. So if you study how many galaxy clusters there are and how big they are in this picture versus this picture versus this picture, you can tell how exactly structure forms. You can see how these structures evolve from small ones early on to big ones later. And you can say, well, I had to have this much matter and this much dark matter and this many photons and this many neutrinos. And you can actually lay out all the components, and you can even figure out how gravity works just from that. By having a model that you think can predict this, you can compare it to what you actually see. So that's what we do. And particularly, we use an effect with the unfortunately daunting name of the thermal Sunyaev-Zeldovich effect. This was figured out by a couple of Russian physicists back in the 60s, Sunyaev and Zeldovich. And the idea is fairly simple, that the CMB is shining all of these extremely uniform, part in 10 to the 5 variations out from its surface, all this light coming at you from everywhere. And if that passes through a big ball of hot gas, well, some of the energy in that hot gas can transfer into the photons. It can reverse Compton scatter, and you can blue shift them. So they change from low energy, longer wavelength, lower frequency microwaves into higher energy, shorter wavelength, higher frequency photons. So you can see this as a sort of shadow on wherever there's material in the universe. So if you look at that map of the cosmic microwave background, you see these little holes knocked in it by structure. Now, That original picture that I showed you, the full sky one, came from a telescope called WMAP. They got around this problem of moisture by building a satellite and launching it into space. That's the best way to get away from moisture. The problem is that this has terrible fuzzy resolution. This is zooming in on a smaller patch, and you can't really see any detail at all because it's expensive to launch large telescopes into space. Planck, which you may have heard about over the last few years, was a follow-up space telescope, which has improved resolution. It's about twice the angular resolution because it had a larger mirror. They just spent more money to launch a larger telescope with better detectors and everything else, but ultimately it was limited by its size. And you can see the resolution improved. You can see a lot more detail in here. But from the ground, we don't have to use a 1-meter dish. We can use a 10-meter dish, which gives us much higher resolution. And this is what that looks like to the South Pole Telescope. Same patch of sky, and you can see all sorts of things pop out. But the bit that I care about is this one. Like, this fuzzy structure is all cosmic microwave background. That's the early, early light. These points are galaxies that are shining out their own microwave light, distant galaxies that are contaminating us, essentially. So more light is easy to get rid of, and just you remove points that look like other galaxies. It's this dark spot where something has removed light that's the mysterious bit. This little spot here, this little hole punched in the map, the shadow on it, is exactly this effect. This is where all the photons that we would have seen got knocked up to a different frequency, so we didn't see them. So you're missing light. So SPT looks around and measures where there are all these holes, and that tells us where all the structure in the universe is. We can then figure out how far away it is, how big they are, everything about how this structure grew. And it's an incredibly sensitive way of doing it because we're using a backlight instead of an emission light. Normally, when people try to measure structure in the universe, you go ahead and you just count up galaxies. You make these maps of galaxies. That's what that early picture that I showed of the large-scale structure was. That gets really hard when you get far away, because things get dimmer as they get farther away. Less of the light hits you. For a backlit object, that's not actually how it works. In an expanding, complicated universe, it doesn't matter how far away that object is. You see the exact same effect. And you can see all the way from here to the end of, well, the beginning, I suppose, of the universe. So using this technique, we can find all of the galaxy clusters. We can figure out everything that was going on. So to actually do cosmology, to extract information about how the universe works, this is basically what we do. We map out the cosmic microwave background, find all the galaxy clusters, put those in this sort of census. We build a catalog of them, figure out how many there were at different distances, at different ages in the universe's history, figure out how they grew up over time, and from that, infer what there must be. That the universe isn't just made up of the matter that we've spent most of our history familiar with and studying. That's less than 5% of everything. It's not just the dark matter, which is otherwise like matter, except that it doesn't care about light, but we can see it gravitationally. We've seen it for decades in galaxies. The bigger portion is this strange thing that we've just titled dark energy as a placeholder. That's just a name that we gave it because it seems to have most of the energy density of the universe in it, and it doesn't care about light. It's dark, and it has energy. Dark energy. It turns out that the US Department of Energy also will fund things when they're called dark energy. So it was a coup, let's say, in naming. So this is sort of the ultimate goal of why we go down there. There is one other responsibility, which they don't really mention. I've said take pictures. Really, it's stay sane. Don't go completely stir-crazy over the 9 months that you're completely isolated and trapped there. And the way I did it was by buying a camera and heading down. Learned how to take pictures while I was there. So I got into photography. The reason that seemed like a good idea was this. This is not a picture I took. Most of the pictures in here I did. This, obviously, not me. This is the aurora australis. Like the northern lights, the aurora borealis, there's a southern light. They form, like the northern lights, in an oval around the magnetic pole. The magnetic poles are misaligned from the geographic poles. They're offset by a few hundred kilometers. And at the South Pole, they're offset just so that the auroras lie directly over the geographic South Pole. In the north, it's offset in an awkward way that leaves the auroras really over uninhabited nowhere. So when you see them, they tend to be off on the horizon. Occasionally, a big auroral storm will come and they'll wash overhead. But at the South Pole, they're constantly there, all the time, directly overhead, running horizon to horizon. So this was my first glimpse of them, just a few weeks after sunset. It's not a particularly impressive one, but it was exciting. That was the first time I'd ever seen aurora of any sort. Growing up in Canada, somehow I never saw an aurora borealis. I also like this one because of this little guy. This windrose on top of the flagpole, which points out that every direction is north. Yes, thanks. So because of that, actually, we don't use north, south, east, west, because the correct answer, if you're trying to go anywhere, is north. Instead, we have what we call grid north, grid east, and it's just a whole new system, not used anywhere else in the world, not recognized by anyone off station, but that's how we describe things. This is what the station looks like when you walk back to it after a long, hard day at the office. Nice auroras glowing overhead. This red glow on the ground is from someone out back working. We keep all our stores and food outside, it's a giant freezer. And when you're outside, like I said, you can't have lights shining out the window, and you can't have headlights on either. You're not allowed any broad spectrum light. You're only allowed one specific color of red light when you're working outside. So most people get by without any sort of headlamps, without any sort of flashlights at all. But for some work, you do need to be able to see things, and there's one particular color of red light that you get used to. Sometimes the storms pick up, and you get nice broad things, bright enough aurora to light up the ground. This is sort of what the walk to work looks like. As you're wandering along, if you turn off to the side, there's an aurora that's running overhead and really bright. The tricky thing here is that it's still minus 70, and I've still got 4 layers of gloves on, and I've still got 3 hats and a hood all pulled together into a ½ centimeter wide gap, so I can't actually see anything. Because you can't wear glasses either, and I didn't have contacts at the time, so I was effectively blind the whole time doing this. You wander around outside with a camera, you set it up, press go, and hope for the best. You can check them that evening, and because every day I would walk to and from telescope a couple of times, once after breakfast, back for lunch, after lunch, back for dinner, usually go out in the evening to fix whatever broke during dinner, and then come back. You have a lot of trips to try and take pictures, which is important because batteries drain in 30 seconds. You press go, and if you're lucky, it finishes the picture. If it's too cold out, it just dies, and that's that. And then you go back inside and you try again. Once I tried to swap a battery, but the stupid little clip on it requires that you not have any mittens on, and that was a bad idea. It didn't work. Occasionally you do run into people outside, and it feels like a momentous occasion. This is what it looks like, just a black silhouette. And again, remember, you've got several things on your face, so you can't actually speak. You can't see hands, you can't see who that is. So when you run into someone, at first everyone's excited, and you're like, oh, and you sort of mumble sounds at each other for a while, and then you realize it's useless. They do actually give you a name tag, as you can no doubt read right there. I'm not sure what they were thinking, but after a while you just give up and you ignore it. People wander by in the night and you just don't talk to them. You do learn to recognize people's walks, though. Their gait is very distinctive, and you get to know who everyone is and how they shout when they fall over. This is the actual commute. Here's the flag line off on the side, walking by a couple of other telescopes and aurora overhead. This is the Milky Way. The Milky Way is incredibly visible all the time while you're down there, at least when the moon's down, so half the time. While the sun's down, so a quarter of the time. But a lot of the time, the Milky Way is just crystal clear, runs directly over, and you have an amazing view. The other thing is nothing rises and sets. You're at the pole, right? Just like it just turns slowly as the Earth rotates. So when you walk outside, you can immediately know what time it is just by looking for the galaxy. You see it going up, and you're like, oh, 4 p.m. It's the world's biggest clock, right? It works beautifully. This is doing work out at the telescope. It's a tough place to have to repair things. Climbing up on there in the dark, in the night, with nothing but your little red flashlight on, just to shovel out some snow that got in, that blew in during the last storm. can be a slightly harrowing experience. And it should be a 3-minute job, but by the time you've bundled up and done everything, it tends to take the entire day. And you spend a long time out looking at this stuff, but I still, it's among the nicer views I've had from an office. Being able to work under the stars like that and having auroras overhead is really a magical experience. This is what the telescope looks like when it's taking those pictures. It stares up, we take 100 pictures a second, and it swings back and forth. That's it. It does that for 5 years. Modulo, every time it breaks, we go repair it and turn it back on. Here are some bright auroras on a moonlit night. This was towards the end of summer, or the end of my winter, just before the sun came up. Because about a week after that, this showed up on the horizon. And after months and months and months without seeing the sun, thinking of the moon coming up every day as your new sun, as just how bright it gets during day, when the actual sun turns up, it's terrifying. It's a lot brighter than you remember it being. It's a lot scarier than you remember it being, and it just sort of slowly looms up on the horizon. And again, it spirals around for weeks, getting brighter and brighter and brighter, and you're convinced any minute now it's going to pop over the horizon, because nothing could be brighter than it already is. Your eyes have adjusted, your brain is adjusted, everything's adjusted. So that by the time that thing comes back, no one really knows how to deal with it, and everyone's gone completely stir-crazy, and it's a bit of a scene. We do have a party at sunrise. Everyone gets together in the galley and has a fancy meal to try and cope with our new sun. When it does come up, you get to see what happened through the winter. The whole landscape is a little bit different. It's not the sort of well-trod where machinery had been driving around all summer. It's all snow-blown flat. In particular, these things have shown up everywhere. These are called sastrugi. When snow blows in one direction, builds up a little bit of a snow pile and packs it down really hard, and then a storm comes in and blows out the other way and carves out under this pack of snow, you end up with this spike that's a few feet high, maybe 5 feet long, and there's a trap under it. And the spike is as hard as concrete because it was packed in for weeks. And then you can notice, here's my footpath from walking along the flag line. Sometimes these would grow across the flag line, and you can't see the ground. You're walking along, happily going to work in the winter, and you step in one, and it hurts a lot. You fall over fairly badly, bash your knee against this, fall into it, and it constantly happens while you're walking around. And you see other people doing this everywhere. Just anytime anyone's walking outside, you just hear a scream, a swear, and a bunch of people rolling around the ground. The snow drifting gets fairly bad. This building is lost. It will drift over a couple of weeks after that completely. This is my walk to work. That snowbank, so these flags are 14-foot flag poles, and they're barely above ground. This showed up one day. It wasn't there one day, and I was walking to work. Great, walk back, walk out the next day, and I kicked it and tripped. I couldn't see that there was a 12-foot snowdrift. And when you trip on a snowdrift, you trip up, and then you kick it again, and trip up and up and up and up to the top, and then you fall off the far side. You only do that once, because you remember it. But it's a surprise. That's what happens. And then one will come, one will disappear. Snowdrifts are, well, the whole landscape is malleable. The first flight comes in, and it's a magical moment, sometime in late October usually, the first flight, which actually is operated by a Canadian company. They fly down an early drop of equipment, resources, fruit. All winter you've had no fresh anything. Everything that you eat has been frozen for probably 4 to 5 years, and usually it's fried. So when the first tomatoes or pineapples show up, everyone loses their mind. They actually have to post armed guards around the Tupperware bin to make sure that no one tries to steal them. They're not heavily armed, they just have arms. Eventually, you do get plopped on a plane, and you get flown out. This is the view from actually a reconnaissance plane a couple days before I left. But when you look back and you see this has been your entire world for the last year. And it's a strange realization that it's tiny. There's nothing there, and there's a lot of nothingness around you. But thankfully, when they fly you out, they don't just drop you off in winter somewhere. They drop you in New Zealand, where it's the dead of summer, and you can relax. Meanwhile, some other poor sod gets taken down for their turn. So I'll stop there. If anyone has questions, I'm happy to take them. house lights up a little. Yes?
How do you generate electricity down there?
There's a power plant as part of the state. So the question is, how do we generate electricity? There's a power plant, thank you, that's built into the station and a backup power plant next to it. It's all diesel. So there were discussions back in, well, the heyday of nuclear power, call it the 60s, about installing a small nuclear plant because then you could fly in fuel once and you'd be done forever. That was vetoed when they realized if it melted through, it would just sink 3 kilometers and good luck. So no, it's all diesel and it's all flown in planes. So that when the planes come in, they're double loaded with fuel and they pump half their fuel off before they fly out. It's a tremendously inefficient thing to do. For every gallon of fuel that we get and burn, it's in gallons because it's a US station, I apologize. So you can think in every liter of fuel that we burn, it costs them 2 liters to get it there. So it's 3 times worse than you would ever hope. Yeah.
One of the challenges you mentioned was how cold it was. And I realized the temperatures that you showed were kind of similar to the temperatures that were out in space. And I know that when astronauts wear spacesuits, sometimes they have technologies that can kind of heat the inside of the spacesuit. Sometimes they have cooling undergarments that can cool things up if they're warm. So why can't the dress that you take employ some sort of that technology to kind of or is there like funding constraints, for instance?
It's a slightly different environment. It is, that or colder in space, but it's a much more rarefied atmosphere. There's essentially no air. So the only way that astronauts lose heat is through radiative. So they glow, or they are shined on, right? It's not that cold air blows across their hand and takes away. So it's a slightly different environment. So they're essentially in a vacuum, and that means that they only have to worry about radiant heat, and you can build certain things to get around that. Here we have to worry about convective and conductive cooling, which makes life a little more difficult. I think the other thing, if you've ever seen astronauts trying to maneuver, it's tough in those things. I don't think it's actually better than what we've come up with, and funding constraints is probably the third reason. That buying astronaut suits for everyone, it would be cool, but I don't see it happening. There's a question up there.
Do you have to get used to the altitude?
Yeah, so it is high enough that the altitude does cause trouble. When you first arrive, you're winded for the first several days, and conversely, when you leave, you feel like Superman. When you get back to New Zealand and you're at sea level, you can just run up mountainsides and not even break a sweat. It's great. Some people do get altitude sickness. It's high enough up that that's an issue, so when you fly in, they try to give you, I'm not sure what the medicine is, it's an anti-altitude sickness medicine. Probably, yeah. That sounds right. But there are occasionally negative reactions to that. So it depends who goes. One of my colleagues went temporarily blind from it. When he got to the South Pole, he couldn't see. And yeah, because they give it to you shortly before you hop on the flight, and then he slowly fades out. He's thinking, what's happening? Thankfully, came back fine a couple of days later, but because of that, they don't force it on you. It's voluntary, and yeah, some people do get altitude sickness and have to be medevaced.
The microwave background radiation, what wavelength is that when it was first emitted? Like, we see it as microwaves, but it's grossly redshifted, right?
Yeah, it's from a redshift of about 1,000, so it's been redshifted 1,000-fold roughly.
Is it visible light when it's first emitted?
There are visible photons in it. It's mostly IR. Because it's about 3,000 Kelvin, the surface, when it emits. So there's a tail of visible light, very red, but yeah.
And how long after the Big Bang was this light emitted? Is this like the 300,000 years when atoms first formed?
Yep, it's the exact same moment. So the CMB was released roughly 380,000 years after the Big Bang. Yeah. So that's an excellent question. I said that in the future, well, as time goes by, space is getting larger. And the question is, how is that possible if it's already infinite? We don't actually know how big it is. The part that we can see is not infinite, because, as I said, as you look farther and farther, you're seeing older and older, and we see a start. So there's a little volume that we can see. There is an observable universe that we have access to, and that's getting larger, everything inside it. It's possible that the universe is infinite, like you say, and that's consistent. That's sort of the baseline model. And yet, it's getting larger. It's a hard thing to think about, something that's infinitely large getting bigger. The only way that you can really think about it is in terms of densities or in the distance between any 2 points. So even if it continues forever off in every direction, any 2 points can still get further apart. And if that does everywhere, then you just have an infinity that's a little bit bigger. Infinity is a tricky thing. I really like that question. Yeah?
Describe again the significance of those dark patches.
Sure, sorry.
The hot gases that change the frequency.
So the only place that those dark patches represent a clump of hot gas. And when I say a clump, I mean a clump of gas that's maybe 1,000 times the mass of our Milky Way. So it's a lot of gas. And it has to be extremely hot gas in order to produce this spectral shift that we see. And the only way that you get that much hot gas is when it's in these largest structures, these clusters of galaxies. So it's really a smoking gun for where there's a cluster of galaxies. So the goal here is just to come up with a census of where there are clusters of galaxies in the universe. If we can find every cluster, that means we found all of the largest structures. And then we can look at how those evolve over time. We can see how the older ones looked, how the newer ones looked, how the newer ones looked. And by tracing that evolution, we can say what processes were at play.
What are the white patches?
The white patches are emissive sources. Let me just jump back to that slide, if I can. Oh, it might be too lit up in here to see it anyway, but let's see. Oh no, you can kind of see. There are these white patches, the sort of salt in the salt and pepper. Those are mostly what we call dusty star-forming galaxies. So they're distant galaxies. We're probably looking about halfway back to the Big Bang to see those. So you're looking very far away, very far back in time. And that's light that's coming from an early generation of stars. So about 7 billion years ago, actually no, it was earlier than that, roughly 11 billion years ago, there was a huge burst of star formation. When the first stars lit up in the universe, a lot of them went off at once. There were a lot more stars being born long ago than there are now. And all the light that they put out warmed things up. And what you're actually seeing there is dust that has been warmed by early stars re-glowing, just glowing their light as hot objects, just the way coals in the fire glow. This is all the dust in early galaxies. It's been heated up by its resident stars, its first stars, and is glowing at you now. So we see that excess glow. Looks like...
Yeah, I'm told that we're running out of time. My name is Joe. I'm the president of the Mississauga Center of the RASC, Royal Astronomical Society of Canada. And on behalf of both the RASC and the RCI, we'd like to thank you very much and present you with a little gift. There's a little card and an ebook of the RCI Centennial Report.
Thank you.
Yeah. So before we sign off and get out of here, I'll quickly mention a couple of meetings coming up. November 24th at the University of Mississauga, we have Tanya Harrison coming to talk about past and present water on Mars. If you haven't had a chance to see the tables out there, the RASC has a couple of things that point you to our website. So we got some meetings mentioned there. The RCI talks, the next talk here, as I understand it, is December 7th, and talking about toys and video games and all sorts of cool stuff and how that relates to education. So by all means, check those out. I think there's some space calendars for sale. And yeah, that's all we wanted to say. Pretty much, yeah. So that's good.
All right. Thank you very much, Joe. Let's give a round of applause to Keith.